Learning objectives. In this chapter, the user will learn the following in detail. Knapsack problem, 0 or 1 knapsack, fractional knapsack, activity selection problem, Huffman's codes, minimum spanning tree, Kruskal's algorithm, Prim's algorithm, Dijkstra's algorithm. Activity selection problem. The activity selection problem for which a greedy algorithm efficiently computes an optimal solution. The problem of scheduling several competing activities that require exclusive use of a common resource with the goal of selecting a maximum size set of mutually compatible activities. Suppose we have a set S which has the elements A1 up to AN of n proposed activities that wish to use a resource such as a lecture hall which can serve only one activity at a time. Each activity AI has a start time Si and a finish time Fi, where 0 less than or equal to Si less than Fi less than infinity. If selected activity AI takes place during the half-open time interval Si Fi. Activities AI and Aj are compatible if the intervals Si Fi and Sj Fj do not overlap. That is, AI and Aj are compatible if Si greater than or equal to Fi or Sj greater than or equal to Fj. In the activity selection problem, we wish to select a maximum size subset of mutually compatible activities. We assume that the activities are sorted in monotonically increasing order of finish time. F1 less than or equal to F2 less than or equal to F3, it's going up to Fn minus 1 less than or equal to Fn. For example, consider the following set S of activities which is shown here. For this example, the subset A3, A9, A11 consists of mutually compatible activities. It is not a maximum subset since the subset A1, A4, A8, A11 is larger. In fact, the set A1, A4, A8 and A11 is the largest subset of mutually compatible activities. Another largest subset is A2, A4, A9 and A11. Solve this problem in several steps. Start by thinking about a dynamic programming solution in which we consider several choices when determining which subproblems to use in an optimal solution. Then observe that we need to consider only one choice, the greedy choice, and that when we make the greedy choice, only one subproblem remains. Based on these observations, we shall develop a recursive greedy algorithm to solve the activity scheduling problem. We shall complete the process of developing a greedy solution by converting the recursive algorithm to an iterative one. Although the steps we shall go through in this section are slightly more involved than is typical when developing a greedy algorithm, they illustrate the relationship between greedy algorithms and dynamic programming. The optimal substructure of the activity selection problem. We can easily verify that the activity selection problem exhibits optimal substructure. Let us denote by Sij. The set of activities that start after activity AI finishes and that finish before activity Aj starts. Suppose that we wish to find a maximum set of mutually compatible activities in Sij, and suppose further that such a maximum set is Aij, which includes some activity Ak. By including Ak in an optimal solution, we are left with two subproblems. Finding mutually compatible activities in the set Sik, activities that start after activity Ai finishes and that finish before activity Ak starts, and finding mutually compatible activities in the set Skj, activities that start after activity Ak finishes and that finish before activity Aj starts. Let Aik equal to Aij intersection Sik and Akj equals Aij intersection Skj, so that Aik contains the activities in Aij that finish before Ak starts and Akj contains the activities in Aij that start after Ak finishes. Thus we have Aij equals Aik union within set Ak union Akj. And so the maximum size set Aij of mutually compatible activities in Sij consists of modulus of Aij equals modulus of Aik plus modulus of Akj plus 1 activities. The usual cut and paste argument shows that the optimal solution Aij must also include optimal solutions to the two subproblems for Sik and Skj. If we would find a set Akj dash of mutually compatible activities in Skj where modulus of Akj dash greater than modulus of Akj, then we would use Akj dash rather than Akj in a solution to the subproblem for Sij. We would have constructed a set of modulus of Aik plus modulus of Akj dash plus 1 greater than modulus of Aik plus modulus of Akj plus 1 equals modulus of Aij. Mutually compatible activities, which contradicts the assumption that Aij is an optimal solution. A symmetric argument applies to the activities in Sik. This way of characterizing optimal substructure suggests that we might solve the activity selection problem by dynamic programming. If we denote the size of an optimal solution for the set Sij by C of ij, then we would have the recurrence C of I, j equal to C of I, k plus C of k, j plus 1. Of course, if we did not know that an optimal solution for the set Sij includes activity Ak, we would have to examine all activities in Sij to find which one to choose, so that C of I, j equal to 0 if Sij equal to null. Max Ak belongs to Sij, C of I, k plus C of k, j plus 1 if Sij not equal to null. We would then develop a recursive algorithm and memorize it, or we would work bottom up and fill in table entries as we go along. But we would be overlooking another important characteristic of the activity selection problem that we can use to great advantage: making the greedy choice. What if we could choose an activity to add to our optimal solution without having to first solve all the subproblems? That would save us from having to consider all the choices inherent in the above recurrence. In fact, for the activity selection problem, we need consider only one choice, the greedy choice. What do we mean by the greedy choice for the activity selection problem? Intuition suggests that we should choose an activity that leaves the resource available for as many other activities as possible. Now, of the activities we end up choosing, one of them must be the first one to finish. Therefore, to choose the activity in S with the earliest finish time, since that would leave the resource available for as many of the activities that follow it as possible. If more than one activity in S has the earliest finish time, then we can choose any such activity. In other words, since the activities are sorted in monotonically increasing order by finish time, the greedy choice is activity A1. Choosing the first activity to finish is not the only way to think of making a greedy choice for this problem. If we make the greedy choice, we have only one remaining subproblem to solve: finding activities that start after A1 finishes. Why don't we have to consider activities that finish before A1 starts? S1 less than F1 and F1 earliest finish time of any activity, and therefore no activity can have a finish time less than or equal to S1. Thus, all activities that are compatible with activity A1 must start after A1 finishes. Furthermore, we have already established that the activity selection problem exhibits optimal substructure. Let Sk, which has Ai belongs to S, such that Si greater than or equal to Fk, be the set of activities that start after activity Ak finishes. If we make the greedy choice of activity A1, then S1 remains as the only subproblem to solve. Optimal substructure tells us that if A1 is in the optimal solution, then an optimal solution to the original problem consists of activity A1 and all the activities in an optimal solution to the subproblem S1. Thus, we see that although we might be able to solve the activity selection problem with dynamic programming, we don't need to. Besides, we have not yet examined whether the activity selection problem even has overlapping subproblems. Instead, we can repeatedly choose the activity that finishes first, keep only the activities compatible with this activity, and repeat until no activities remain. Moreover, because we always choose the activity with the earliest finish time, the finish times of the activities we choose must strictly increase. We can consider each activity just once overall in monotonically increasing order of finish times. An algorithm to solve the activity selection problem does not need to work bottom-up like a table-based dynamic programming algorithm. Instead, it can work top-down, choosing an activity to put into the optimal solution and then solving the subproblem of choosing activities from those that are compatible with those already chosen. Greedy algorithms typically have this top-down design: make a choice and then solve a subproblem, rather than the bottom-up technique of solving subproblems before making a choice. Recursive greedy algorithm. We have seen how to bypass the dynamic programming approach and instead use a top-down greedy algorithm. We can write a straightforward recursive procedure to solve the activity selection problem. The procedure, recursive activity selector, takes the start and finish times of the activities, represented as array S and F, the index k that defines the subproblem Sk it is to solve, and the size n of the original problem. It returns a maximum size set of mutually compatible activities in Sk. Assume that the n input activities are already ordered by monotonically increasing finish time. If not, we can sort them into this order in big O of n log n time, breaking ties arbitrarily. In order to start, we add the fictitious activity A0 with F0 equal to 0, so that subproblem S0 is the entire set of activities S. The initial call, which solves the entire problem, is recursive activity selector. The recursive activity selector procedure is shown here. This figure shows the operations of the recursive activity selector algorithm. The operation of recursive activity selector on the 11 activities given. Activities considered in each recursive call appear between horizontal lines. The fictitious activity A0 finishes at time 0 and the initial call recursive activity selector S, F, 0, 11 selects activity A1. In each recursive call, the activities that have already been selected are shaded and the activity shown in white is being considered. If the starting time of an activity occurs before the finish time of the most recently added activity, the arrow between them points left. It is rejected. Otherwise, the arrow points directly up or to the right. It is selected. The last recursive call, the recursive activity selector of S, F, 11, returns null. The resulting set of selected activities is A1, A4, A8 and A11. In a given recursive call, recursive activity selector S, F, K, N, the while loop of lines 2 to 3 looks for the first activity in Sk to finish. The loop examines Ak plus 1 up to An until it finds the first activity Am that is compatible with Ak. Such an activity has Sm greater than or equal to Fk. If the loop terminates because it finds such an activity, line 5 returns the union of Am and the maximum size subset of Sm returned by the recursive call. Recursive activity selector S, F, M and N. Alternatively, the loop may terminate because M greater than N, in which case we have examined all activities in Sk without finding one that is compatible with Ak. In this case, Sk equal to null, and so the procedure returns null in line 6. Assuming that the activities have already been sorted by finish times, the running time of the call recursive activity selector S, F, 0 and N. Over all recursive calls, each activity is examined exactly once in a while loop test of line 2. In particular, activity AI is examined in the last call made in which k less than I. Iterative greedy algorithm. We easily can convert a recursive procedure to an iterative one. The procedure recursive activity selector is almost tail recursive. It ends with a recursive call to itself followed by a union operation. It is usually a straightforward task to transform a tail recursive procedure to an iterative form. In fact, some compilers for certain programming languages perform this task automatically. As written, recursive activity selector works for subproblems Sk, that is, subproblems that consist of the last activities to finish. The procedure greedy activity selector is an iterative version of the procedure recursive activity selector. It also assumes that the input activities are ordered by monotonically increasing finish time. It collects selected activities into a set A and returns this set when it is done. The greedy activity selector procedure is shown in this figure. This procedure works as follows. The variable k indexes the most recent addition to A, corresponding to the activity AK in the recursive version. Since we consider the activities in order of monotonically increasing finish time Fk is always the maximum finish time of any activity in A, that is, Fk equal to max of Fi such that Ai belongs to A. Lines 2 to 3 select activity A1. Initialize A to contain just this activity and initialize K to index this activity. The for loop of lines 4 to 7 finds the earliest activity in Sk to finish. The loop considers each activity Am in turn and adds Am to A. If it is compatible with all previously selected activities, such an activity is the earliest in Sk to finish. To see whether activity Am is compatible with every activity currently in A, in line 5, that its start time Sm is not earlier than the finish time Fk of the activity most recently added to A. If activity Am is compatible, then line 6 to 7 add activity Am to A and set K to M. The set A returned by the call greedy activity selector S, F is precisely the set returned by the call recursive activity selector of S, F, 0 and N. Like the recursive version, greedy activity selector schedules a set of n activities in theta of n time, assuming that the activities were already sorted initially by their finish times. Dijkstra's algorithm. The general method to solve the single source shortest path problem is known as Dijkstra's algorithm. Greedy algorithms generally solve a problem in stages by doing what appears to be the best thing at each stage. For example, to make change in US currency, most people count out the quarters first, then the dimes, nickels, and pennies. This greedy algorithm gives change using the minimum number of coins. The main problem with greedy algorithms is that they do not always work. The addition of a 12-cent piece breaks the coin changing algorithm for returning 15 cents because the answer it gives, 1 12-cent piece and 3 pennies, is not optimal, 1 dime and 1 nickel. Each vertex is marked as either known or unknown. A tentative distance dv is kept for each vertex. This distance turns out to be the shortest path length from S to V using only known vertices as intermediates. As before, we record PV, which is the last vertex to cause a change to dv. Dijkstra's algorithm proceeds in stages, just like the unweighted shortest path algorithm. At each stage, Dijkstra's algorithm selects a vertex V which has the smallest dv among all the unknown vertices and declares that the shortest path from S to V is known. The remainder of a stage consists of updating the values of dw. In the unweighted case, we set dw equal to dv plus 1 if dw equal to infinity. Thus, we essentially lowered the value of dw if vertex V offered a shorter path. If we apply the same logic to the weighted case, then we should set dw equal to dv plus cvw, if this new value for dw would be an improvement. Put simply, the algorithm decides whether or not it is a good idea to use v on the path to w. The original cost, dw, is the cost without using v. The cost calculated above is the cheapest path using v and only known vertices. This graph is our example. This figure represents the initial configuration, assuming that the start node S is vertex v1. Initial configuration table is shown in this figure. The first vertex selected is v1 with path length 0. This vertex is marked known. Now that v1 is known, some entries need to be adjusted. The vertices adjacent to v1 are v2 and v4. Both these vertices get their entries adjusted as indicated in this figure. Next, v4 is selected and marked known. Vertices v3, v5, v6 and v7 are adjacent, and it turns out that all require adjusting as shown in this figure. Then next, v2 is selected. v4 is adjacent but already known, so no work is performed on it. v5 is adjacent but not adjusted because the cost of going through v2 is 2 plus 10 equal to 12 and a path of length 3 is already known. The next vertex selected is v5 at cost 3. v7 is the only adjacent vertex, but it is not adjusted because 3 plus 6 greater than 5. Then v3 is selected and the distance for v6 is adjusted down to 3 plus 5 equal to 8. This figure shows after the vertex v3 is selected. The resulting table is depicted in this figure. Then next, v7 is selected. v6 gets updated down to 5 plus 1 equals 6. The resulting table is shown in this figure. Finally, v6 is selected and this edge marked as known and vertex updated. The final table shows that all edges in a given graph are selected and all vertices marked as known in this figure. To print out the actual path from a start vertex to some vertex v, we can write a recursive routine to follow the trail left in the p variables. In pseudocode to implement Dijkstra's algorithm, each vertex stores various data members that are used in the algorithm. This is shown in this figure. Pseudocode of vertex class for Dijkstra's algorithm is shown here. Routine to print the actual shortest path. The path can be printed out using the recursive routine in this figure. The routine recursively prints the path all the way up to the vertex before v on the path and then just prints v. This works because the path is simple. This figure shows the main algorithm, which is just a for loop to fill up the table using the greedy selection rule. The pseudocode for Dijkstra's algorithm is shown here. A proof by contradiction will show that this algorithm always works as long as no edge has a negative cost. If any edge has negative cost, the algorithm would produce the wrong answer. The running time depends on how the vertices are manipulated, which we have yet to consider. If we use the obvious algorithm of sequentially scanning the vertices to find the minimum dv, each phase will take big O of mod v time to find the minimum, and thus big O of mod v squared time will be spent finding the minimum over the course of the algorithm. The time for updating dw is constant per update and there is at most one update per edge for a total of big O of mod E. Thus, the total running time is big O of mod E plus mod V square equal to big O of modulus of V square. If the graph is dense with mod E equals big theta of mod V square, this algorithm is not only simple but also essentially optimal since it runs in time linear in the number of edges. If the graph is sparse with mod E equal to theta of mod V, this algorithm is too slow. In this case, the distances would need to be kept in a priority queue. There are actually two ways to do this. Both are similar. Selection of the vertex V is a delete min operation. Since once the unknown minimum vertex is found, it is no longer unknown and must be removed from further consideration. The update of W's distance can be implemented two ways. One way treats the update as a decrease key operation. The time to find the minimum is then big O of log mod V, as is the time to perform updates, which amount to decrease key operations. This gives a running time of big O of mod E log mod V plus mod V log mod V equals big O of mod E log mod V, an improvement over the previous bound for sparse graph. Since priority queues do not efficiently support the find operation, the location in the priority queue of each value of Di will need to be maintained and updated whenever Di changes in the priority queue. If the priority queue is implemented by a binary heap, this will be messy. If a pairing heap is used, the code is not too bad. An alternate method is to insert W and the new value dW into the priority queue every time W's distance changes. Thus, there may be more than one representative for each vertex in the priority queue. When the delete min operation removes the smallest vertex from the priority queue, it must be checked to make sure that it is not already known, and if it is simply ignored and another delete min is performed. Although this method is superior from a software point of view and is certainly much easier to code, the size of the priority queue would get to be as large as modulus of E. This does not affect the asymptotic time bounds since modulus of E less than or equal to modulus of V square implies that log modulus of E less than or equal to 2 log modulus of V. Thus, we still get an big O of modulus E log modulus of V algorithm. However, the space requirement does increase, and this would be important in some applications. Moreover, because this method requires modulus of E delete mins instead of only modulus of V, it is likely to be slower in practice. Notice that for the typical problems such as computer mail and mass transit commutes, the graphs are typically very sparse because most vertices have only a couple of edges. So it's important in many applications to use a priority queue to solve this problem. There are better time bounds possible using Dijkstra's algorithm if different data structures are used. When Fibonacci heaps is used, the running time is big O of modulus of E plus mod V log mod V. Fibonacci heaps have good theoretical time bounds but a fair amount of overhead. So it's not clear whether using Fibonacci heaps is actually better in practice than Dijkstra's algorithm with binary heaps. To date, there are no meaningful average case results for this problem. Fractional knapsack problem. The setup is the same as the 0 or 1 knapsack problem, but the thief can take fractions of items rather than having to make a binary 0, 1 choice for each item. You can think of an item in the 0 or 1 knapsack problem as being like a gold ingot, and an item in the fractional knapsack problem as more like gold dust. Both knapsack problems exhibit the optimal substructure property. Consider the given set S of n items such that each item I has a positive benefit Bi and a positive weight Wi, and to find the maximum benefit subset that does not exceed a given weight W. If we restricted to entirely accepting or rejecting each item, then we would have the 0 or 1 version of this problem. Let us now allow ourselves to take arbitrary fractions of some elements. The motivation for this fractional knapsack problem is that we are going on a trip and we have a single knapsack that can carry items that together have weight at most W. In addition, allowed to break items into fractions arbitrarily. That is, we can take an amount xi of each item I such that 0 less than or equal to xi less than or equal to wi for each I belongs to S, and summation of I belongs to S xi less than or equal to w. The total benefit of the items taken is determined by the objective function. Summation of I belongs to S bi of xi by wi. Consider an example. A student who is going to an outdoor sporting event and must fill a knapsack full of foodstuffs to take along. Each candidate foodstuff is something that can be easily divided into fractions such as soda puff, potato chips, popcorn, and pizza. The following figure represents the greedy algorithm for the fractional knapsack problem. Algorithm: fractional knapsack. Input: set S of items such that each item I belongs to S has a positive benefit Bi and a positive weight Wi, positive maximum total weight W. Output: amount Xi of each item I belongs to S that maximizes the total benefit while not exceeding the maximum total weight W. Then the procedure is shown here. This is one place where greed is good, for we can solve the fractional knapsack problem using the greedy approach, which is given in this algorithm. The fractional knapsack algorithm can be implemented in big O of n log n time, where n is the number of items in S. Specifically, we use a heap-based property Q to store the items of S, where the key of each item is its value index. With this data structure, each greedy choice which removes the item with greatest value index takes big O of log n time. To see that the fractional knapsack problem satisfies the greedy choice property, suppose that there are two items I and j such that xi less than wi, xi greater than 0 and vi less than vj. Let y equal to min of wi minus xi, xj. Replace an amount y of item j and equal amount of item I, thus increasing the total benefit without changing the total weight. Therefore, we can correctly compute optimal amounts for the items by greedily choosing items with the largest value index. Huffman scores. Huffman codes compress data very effectively. Savings of 20% to 90% are depending on the characteristics of the data being compressed. We consider the data to be a sequence of characters. Huffman's greedy algorithm uses a table giving how often each character occurs, that is, its frequency, to build up an optimal way of representing each character as a binary string. Suppose we have a 100,000 character data file that we wish to store compactly. We observe that the characters in the file occur with the frequencies given by the following figure of a character coding problem. This is a data file of 100,000 characters, contains only the characters A to F with the frequencies indicated. If we assign each character a 3-bit code word, we can encode the file in 300,000 bits. Using the variable length code shown, we can encode the file in only 224,000 bits. That is, only 6 different characters appear and the character occurs 45,000 times. We have many options for how to represent such a file of information. Here, we consider the problem of designing a binary character code, or code for short, in which each character is represented by a unique binary string, which we call a code word. If we use a fixed length code, we need 3 bits to represent 6 characters. A is 000, B is 001, and up to F equal to 101. This method requires 300,000 bits to code the entire file. Can we do better? A variable length code can do considerably better than a fixed length code by giving frequent characters short code words and infrequent characters long code words. Given figure shows such a code. Here the 1-bit string 0 represents A and the 4-bit string 1100 represents F. This code requires to represent the file a savings of approximately 25%. In fact, this is an optimal character code for this file. Prefix codes. We consider here only codes in which no code word is also a prefix of some other code word. Such codes are called prefix codes. Although we won't prove it here, a prefix code can always achieve the optimal data compression among any character code, and so we suffer no loss of generality by restricting our attention to prefix codes. Encoding is always simple for any binary character code. Concatenate the code words representing each character of the file. For example, with the variable length prefix code shown in this figure, code the 3-character file ABC as 0.101.100 equals 0101.100, where dot denotes concatenation. Prefix codes are desirable because they simplify decoding. Since no code word is a prefix of any other, the code word that begins an encoded file is unambiguous. We can simply identify the initial code word, translate it back to the original character, and repeat the decoding process on the remainder of the encoded file. In our example, the string 001.01101 pauses uniquely as 0.0.101.1101, which decodes to AABE. The decoding process needs a convenient representation for the prefix code so that we can easily pick off the initial code word. A binary tree whose leaves are the given characters provides one such representation. We interpret the binary code word for a character as the simple path from the root to that character, where 0 means go to the left child and 1 means go to the right child. This figure shows the trees for the 2 codes of our example for the given coding scheme. Note that these are not binary search trees, since the leaves need not appear in sorted order and internal nodes do not contain character keys. Each leaf is labeled with the character and its frequency of occurrence. Each internal node is labeled with the sum of the frequencies of the leaves in its subtree. This figure shows the tree corresponding to the fixed length code A equal to 000. It goes up to F equal to 101. This figure shows the tree corresponding to the optimal prefix code A equal to 0, B equal to 101 and it goes up to F equal to 1100. An optimal code for a file is always represented by a full binary tree in which every non-leaf node has two children. The fixed length code in our example is not optimal since it's tree. This figure is not a full binary tree. It contains code words beginning 10 but none beginning 11. Since we can now restrict our attention to full binary trees, if C is the alphabet from which the characters are drawn and all character frequencies are positive, then the tree for an optimal prefix code has exactly modulus of C leaves, one for each letter of the alphabet and exactly mod C minus 1 internal nodes. Given a tree T corresponding to a prefix code, we can easily compute the number of bits required to encode a file. For each character C in the alphabet C, let the attribute C, F or EQ denote the frequency of C in the file and let dt of C denote the depth of C's leaf in the tree. Note that dt of C is also the length of the code word for character C. The number of bits required to encode a file as follows, which we define as the cost of the tree T. Constructing a Huffman code. Huffman invented a greedy algorithm that constructs an optimal prefix code called a Huffman code. Its proof of correctness relies on the greedy choice property and optimal substructure. This figure shows the Huffman's algorithm. In this algorithm, we assume that C is a set of n characters and that each character C belongs to capital C is an object with an attribute C.frequency giving its frequency. The algorithm builds the tree T corresponding to the optimal code in a bottom-up manner. It begins with a set of modulus of C leaves and performs a sequence of mod C minus 1 merging operations to create the final tree. The algorithm uses a min priority queue keyed on the frequency attribute to identify the two least frequent objects to merge together. When we merge two objects, the result is a new object whose frequency is the sum of the frequencies of the two objects that were merged. The steps of Huffman's algorithm for the frequencies given in this figure. Each part of this figure shows the contents of the queue sorted into increasing order by frequency. At each step, the two trees with lowest frequencies are merged. Leaves are shown as rectangles containing a character and its frequency. Internal nodes are shown as circles containing the sum of the frequencies of their children. An edge connecting to an internal node with its children is labeled 0 if it is an edge to a left child and 1 if it is an edge to a right child. The code word for a letter is the sequence of labels on the edges connecting the root to the leaf for that letter. This figure shows the initial set of n equal to 6 nodes, one for each letter. From Part B to Part E shows the intermediate stages. Part F shows the final tree. Since the alphabet contains 6 letters, the initial queue size is n equal to 6 and 5 merge steps build the tree. The final tree represents the optimal prefix code. The code word for a letter is the sequence of edge labels on the simple path from the root to the letter. Line 2 initializes the min priority queue with the characters in C. The for loop in lines 3 to 8 repeatedly extracts the two nodes X and Y of lowest frequency from the queue, replacing them in the queue with a new node Z representing their merger. The frequency of Z is computed as the sum of the frequencies of X and Y in line 7. The node Z has X as its left child and Y as its right child. This order is arbitrary. Switching the left and right child of any node yields a different code of the same cost. After n-1 merges, line 9 returns the one node left in the queue, which is the root of the code tree. Although the algorithm would produce the same result if we were to excise the variables x and y, assigning directly to z.left and z.right in lines 5 and 6, and changing line 7 to z.frequency equal to z.left.frequency plus z.right.frequency. We shall use the node names x and y in the proof of correctness. Therefore, we find it convenient to leave them in. To analyze the running time of Huffman's algorithm, we assume that Q is implemented as a binary min heap. For a set C of n characters, we can initialize Q in line 2 in big O of n time. The for loop in lines 3 to 8 executes exactly n-1 times, and since each heap operation requires time big O of log n, the loop contributes big O of n log n to the running time. Thus, the total running time of Huffman on a set of n characters is big O of n log n. Knapsack problem and 0-1 knapsack problem. The knapsack problem: a thief robbing a store finds n items. The ith item is worth VI dollars and weighs WI pounds, where VI and WI are integers. The thief wants to take as valuable a load as possible, but he can carry at most W pounds in his knapsack for some integer W. Which items we select? We call this the 0-1 knapsack problem because for each item, the thief must either take it or leave it behind. He cannot take a fractional amount of an item or take an item more than once. For the 0 or 1 knapsack problem, consider the most valuable load that weighs at most W pounds. If we remove item J from this load, the remaining load must be most valuable load weighing at most W minus Wj that the thief can take from the n-1 original items excluding J. For the comparable fractional problem, consider that if we remove a weight W of one item J from the optimal load, the remaining load must be the most valuable load weighing at most W minus small w that the thief can take from the n-1 original items plus Wj minus W pounds of item J. Although the problems are similar, we can solve the fractional knapsack problem by a greedy strategy, but we cannot solve the 0 or 1 problem by greedy strategy. To solve the fractional problem, First compute the value per pound VI by WI for each item. Obeying a greedy strategy, the thief begins by taking as much as possible of the item with the greatest value per pound. If the supply of that item is exhausted and he can still carry more, he takes as much as possible of the item with the next greatest value per pound, and so forth, until he reaches his weight limit W. Thus, by sorting the items by value per pound, the greedy algorithm runs in big O of n log n time. We leave the proof that the fractional knapsack problem has the greedy choice property. To see that this greedy strategy does not work for the 0-1 knapsack problem, consider the problem instance illustrated in this figure. As an example showing that the greedy strategy does not work for the 0-1 knapsack problem. In this figure shows the thief must select a subset of the 3 items shown whose weight must not exceed 50 pounds. In this figure shows optimal subset includes item 2 and 3. Any solution with item 1 is suboptimal even though item 1 has the greatest value per pound. In this figure, the fractional knapsack problem, taking the items in order of greatest value per pound, yields an optimal solution. This example has 3 items and a knapsack that can hold 50 pounds. Item 1 weighs 10 pounds and it's worth $60. Item 2 weighs 20 pounds and it's worth $100. Item 3 weighs 30 pounds and it's worth $120. Thus, the value per pound of item 1 is $6 per pound, which is greater than the value per pound of either item 2, $5 per pound, or item 3, $4 per pound. The greedy strategy would take item 1 first. As you can see from the case analysis in this figure, the optimal solution takes items 2 and 3, leaving item 1 behind. The 2 possible solutions that take item 1 are both suboptimal. For the comparable fractional problem, the greedy strategy, which takes item 1 first, does yield an optimal solution, as shown in this figure. Taking item 1 does not work in the 0 or 1 problem because the thief is unable to fill his knapsack to capacity and the empty space lowers the effective value per pound of his load. In the 0 or 1 problem, when we consider whether to include an item in the knapsack, we must compare the solution to the subproblem that includes the item with the solution to the subproblem that excludes the item before we can make the choice. The problem formulated in this way gives rise to many overlapping subproblems. A hallmark of dynamic programming use dynamic programming to solve the 0 or 1 problem. Kruskal's algorithm. Continually select the edges in order of smallest weight and accept an edge if it does not cause a cycle. Kruskal's algorithm maintains a forest, that is a collection of trees. Initially, there are modulus of V single node trees. Adding an edge merges 2 trees into 1. The initial structure is shown in this figure. The algorithm terminates when enough edges are accepted and now there is only one tree, that is the minimum spanning tree. Function Kruskal in Kruskal's algorithm used to find a minimum spanning tree. Pseudocode for Kruskal's algorithm is shown in this figure. It turns out to be simple to decide whether edge u, v should be accepted or rejected. The invariant we will use is that at any point in the process, two vertices belong to the same set if and only if they are connected in the current spanning forest. Thus, each vertex is initially in its own set. If u and v are in the same set, the edge is rejected because since they are already connected, adding u, v would form a cycle. Otherwise, the edge is accepted and a union is performed on the two sets containing u and v. It is easy to see that this maintains the set invariant because once the edge u, v is added to the spanning forest, if w was connected to u and x was connected to v, then x and w must now be connected and thus belong in the same set. The edges would be sorted to facilitate the selection, but building a heap in linear time is a much better idea. The delete means give the edges to be tested in order. Typically, only a small fraction of the edges need to be tested before the algorithm can terminate, although it is always possible that all the edges must be tried. For instance, if there was an extra vertex v8 and edge v5, v8 of cost 100, all the edges would have to be examined. The worst case running time of this algorithm is big O of modulus of E log modulus of E, which is dominated by the heap operations. Notice that since modulus of E equal to big O of modulus of V squared, this running time is actually big O of mod E log mod V. In practice, the algorithm is much faster than this time bound would indicate. Example of Kruskal's algorithm. The following figures shows the order in which edges are added to the forest. Sort the edges by increasing edge weight. It shows the empty tree. It does not contain any node included in the set. Select first mod v minus 1 edges which do not generate a cycle. In this figure, the edge v1 and v4 is accepted and connect those vertices. Then next, accept the edge E of v6, v7 and add these nodes in minimum spanning tree. Then next, accept the edge v1, v2 and adds this with minimum spanning tree. Next, accept the edge v3 and v4 and add this edge with minimum spanning tree. Next, accept the edge v4 and v7 and add this edge with minimum spanning tree. Finally, include the edge v7 and v5 and add this edge with minimum spanning tree. All vertices are added into the spanning tree. No more unvisited vertices are there to include. Minimum spanning tree. A spanning tree of an undirected graph G is a subgraph of G, that is a tree containing all the vertices of G. A minimum spanning tree MST for a weighted undirected graph is a spanning tree with minimum weight. In a weighted graph, the weight of a subgraph is the sum of the weights of the edges in the subgraph. A spanning tree of G is a subgraph T that is connected, acyclic, includes all of the vertices. Minimum spanning tree. Graph is connected. Edge weights are distinct. Input. Undirected graph G with positive edge weights connected. Goal. Find a min-weight set of edges that connects all of the vertices. Consequence. MST exists and is unique. Greedy algorithm for minimum spanning tree. Step 1. Order the edges in increasing weight. Step 2. While the graph is not connected, add an edge. Step 3. End. When all vertices are connected. The algorithm can be halted as soon as n-1 edges. Search in MST. List all connected subgraphs of G. Return subgraph with least weight, number of vertices n, and the number of edges m. Big O of m power n-1 is total running time of this search. Brute force. In brute force method, try all possible spanning trees. Issues of minimum spanning tree. Not so easy to implement. Far too many of them. Cut property of minimum spanning tree. A cut in a graph is a partition of its vertices into two non-empty sets. A crossing edge connects a vertex in one set with a vertex in the other. Cut property. Given any cut, the crossing edge of min weight is in the minimum spanning tree. This figure shows crossing edge separating grey and white vertices, and minimum weight crossing edge must be in the minimum spanning tree. Cut property. Correctness proof, as shown in this figure. Suppose min weight crossing edge E is not in the minimum spanning tree. Adding E to the minimum spanning tree creates a cycle. Some other edge F in cycle must be a crossing edge. Removing F and adding E is also a spanning tree. Since weight of E is less than the weight of F, that spanning tree is lower weight. Greedy algorithm. Example of is shown here. The initial graph is shown in this figure. List of edges for initial graph is shown in this table. Start with G dash equal to V, null and sorted the list of edges as shown in this figure. Sorted list of edges shown in this table. Add edge AB from list to graph. If no cycles are created, remove this edge from list. Sorted list of edges after removing the edge AB from this graph is shown in this table. Add edges DF and CD from list to graph. If no cycles are created, remove edge from list. Sorted list of edges after removing the added edges is shown in this table. Now the sorted list of edges is shown in this table. Check for cycles using depth first search starting at a vertex in the added edge. Start at C, then C visits D, D visits F, and F again visits C. So here, the vertex C gets visited twice. A cycle exists, so the edge CF should not be added to the graph. End. When all vertices can be visited. Graph is connected. After that, the sorted list of edges is shown in this table. Now the sorted list of edges is shown in this table. Check for cycles using depth first search starting at a vertex in the added edge. Here start at B, The vertex B visits D, and D visits C visits F, and F again visits A. If all vertices are visited by DFS, then the graph is connected and we are done. Sorted list of edge is shown in this table. Check for cycles using depth first search, starting at a vertex in the added edge. Start at E. The vertex E visits F, F visits D, D visits B, B visits A, and A visits C. All vertices are visited and there were no cycles. We have found a minimum spanning tree with weight 12. Prime's algorithm. One way to compute a minimum spanning tree is to grow the tree in successive stages. In each stage, one node is picked as the root and we add an edge and thus an associated vertex to the tree. At any point in the algorithm, we can see that we have a set of vertices that have already been included in the tree. The rest of the vertices have not. The algorithm finds at each stage a new vertex to add to the tree by choosing the edge u, v, such that the cost of uv is the smallest among all edges where u is in the tree and v is not. This figure shows how this algorithm would build the minimum spanning tree, starting from the vertex v1. Initially, v1 is in the tree as a root with no edges. Each step adds one edge and one vertex to the tree. We can see that Prime's algorithm is essentially identical to Dijkstra's algorithm for shortest paths. As before, for each vertex, we keep value dv and pv and an indication of whether it is known or unknown. dv is the weight of the shortest edge connecting v to a known vertex, and pv, as before, is the last vertex to cause a change in dv. The rest of the algorithm is exactly the same, with the exception that since the definition of dv is different, so is the update rule. For this problem, the update rule is even simpler than before. After a vertex v is selected, for each unknown w adjacent to v, dw equal to min of dw, cw, v. The initial configuration of the table used in Prime's algorithm is shown in this figure. After v1 is declared known and v2, v3 and v4 are updated, the table resulting from this is shown in this figure. This table shows the results after v4 is declared known. Selected vertex is v4. Every vertex is adjacent to v4 is examined, but v1 is not examined because it is known. v2 is unchanged because it has dv equal to 2 and the edge cost from v4 to v2 is 3. All the rest are updated. The next vertex chosen is v2, arbitrarily breaking a tie. This does not affect any distances. Then v3 is chosen, which affects the distance in v6, producing the result which is shown in this figure. This table shows the result from the selection of v7, which forces v6 and v5 to be adjusted. This table shows after v6 and then v5 are selected, Prime's algorithm terminates here. This is the final table. The edges in the spanning tree can be read from the table. v2, v1, v3, v4, v4, v1, v5, v7, v6, v7 and v7, v4. The total cost is 16. Be aware that the Prime's algorithm runs on undirected graphs, so when coding it, remember to put every edge in two adjacency lists. The running time is big O of modulus of V square without heaps, which is optimal for dense graphs, and big O of mod E log mod V using binary heaps, which is good for sparse graphs. Conclusion. In this chapter, we have covered the following in detail. Knapsack problem, 0/1 knapsack problem, fractional knapsack problem, activity selection problem, Huffman's codes, minimum spanning tree algorithm, Kruskal's algorithm, Prim's algorithm, Dijkstra's algorithm.